Hey there guys, in this video I want to talk about centripetal acceleration. Not centripetal acceleration, that's what we talked about last week. This week we're going to talk about centripetal force, okay? Centripetal force, which is, you can't really talk about centripetal acceleration without also talking about centripetal force. They kind of go together, they're one and the same thing, because you're getting a centripetal acceleration because of a centripetal force, essentially. So let's say that we take the example that we were talking about last week, which is a person that is, let's say, holding on to a string. Let's say they're holding on to a yo-yo, okay? And here's the string from the yo-yo. They're holding it like this, and they're swinging it around their head. So above their head, they're just swinging it in a circle like this. Okay, so like this above their head, and so it's going in this direction as it's swinging. And we learned last week that anytime that we've got an object that is moving in a circle like this, we said that the acceleration that it feels is always towards the center of the circle. So the centripetal acceleration is the acceleration that this object feels towards the center of this circle as it moves around. So even though it's got a constant velocity in the sense of like its speed moving around here, in the sense of its direction, it's actually accelerating the entire time because it's constantly changing its direction of motion. And so it's always accelerating towards the center of the circle. Well, now let's think about centripetal force then. Let's think about the centripetal force. So let me redraw this down here. So let's say here's the yo-yo. All right. Here's the string that it's attached to. Person holding on to it. There's their arm. Here's the string. All right. Now let's just label the forces that this object would feel. Okay. So we know that it's going to feel a force of gravity from the earth pulling down on it. It's also going to have normal force, which is really also from the string kind of pulling it in. And it's also going to feel this force from the string, right? There's going to be anytime we have a force from like a string or a rope, we call that a force of tension. A force of tension. And so it feels that force of tension pulling in this way the entire time. Now here's the other interesting thing is that you might also want to think that there's also a force going this way, right? There might be a force going this way because even if like you're on like let's say you're on like what's a ride at the fair, something like the Gravitron or something like that. When you're spinning in a circle, you feel like there's something pushing or pulling you out this way. And that's referred to centrifugal force, which really isn't a force. It's just the feeling of your body wanting to continue in that straight line path because of Newton's first law, right? So because of inertia, you want to continue moving that way, but there's no force pushing or pulling you that way. Your body just wants to continue that way, but it's being kept from going that way because of this centripetal force. So there actually is no force pushing or pulling you that way. There is nothing. You feel like you want to move that way because of the fact, basically, that you're accelerating this way. Your body wants to continue moving that way, and so you feel that, but you're centripetally accelerating, so you are continually getting pulled this way, even though your body wants to continually move that way. It's kind of a weird thing to think about, but that idea of centrifugal force really isn't a force, and so you shouldn't have it on your force diagram, even though you're kind of feeling that your body wants to continue that way. It's not a force, and so we shouldn't have that on there. Again, I know it's kind of a weird thing to think about, that centrifugal force, but centrifugal force, by the way, is like in reference to like if you take like a like let's say you had let's say this was a cup of water, okay? If you had a cup of water attached to the string and you were to like swing it over your head, the water is not going to fall out due to that centrifugal force, which again is just the water wanting to continue away from the center. It wants to continue to move away from it, but it can't because of this centripetal force that's constantly accelerating it this way. But again, the main thing here, if you're kind of still confused on that, the main thing we want to know is that there's no force this way, okay? Because if there was a force, then it would be, that would kind of maybe balance this out, and then it wouldn't be accelerating, right? We know that if something is accelerating, there has to be an unbalanced force, there has to be a net force, which is what we have. So there's no force this way in this case. So that leads us to showing that the centripetal force in this case is the string. It's you, the string, the force of tension from the string pulling the yo-yo this way. That is the centripetal force. So basically, for the centripetal force, it's the force that we'll just say goes toward the center of the circle. The force that goes towards the center of the circle is the centripetal force. So basically what that means is the centripetal force could be a lot of different things. It depends on the situation at hand. So like in this situation, the centripetal force is the force of tension. So they're not two different forces. It's not like I can say there's a force of tension and there's also a centripetal force. No, that's not right. The centripetal force is the force of tension in this case. So for this, the centripetal force is the force of tension in this case. But that's not all circular moving objects are doing that because of a force of tension. It depends on the situation, right? So the centripetal force could very well be the force of gravity. Like if thinking about the moon being pulled by the Earth as it's moving in a circular orbit around the Earth, that's the force of gravity that's actually providing the centripetal force in that case. Centripetal force could be maybe like an applied force. So going back to the example I mentioned earlier about a ride, I don't know if this is still a ride, but the gravitron, so like you're basically sitting in this would be like looking down. This would be the top view, looking down on it, and people are like standing. You like stand along the edge of this thing. Okay, so these are the people's tops of their heads. And this thing just spins at a really high rate. And in this case, the centripetal force would actually be this thing behind you pushing you this way, technically, would be providing the centripetal force as this thing spins around the back wall of this. So the applied force pushing you inwards would be the centripetal force. So it could be a force applied. It could also be a force of friction. So like if a car is going around a corner, what force, so let's say there's, again, we'll just say this is the corner of the road right here. Here's the car. And again, looking at the top, so this is like the top of the car looking down, and it's going around this corner here. Well, as it's going around the corner, what is the thing that's pushing it towards the center of the corner? And it would be the friction from the road. The friction between the wheels and the road. As you turn the wheels, the road pushes back, and it's pushing you towards the center of the circle. And so centripetal force in that case would be the force of friction. So again, the main thing here is that centripetal force could be a lot of different things. It's whatever force is pushing or pulling that thing towards the center of that circle, basically. Okay, so that's the main thing to keep in mind. Centripetal force could be a lot of different forces. It just depends on the situation. In this situation, it's the force of tension on the string is what's providing the centripetal force. All right, so now how about trying to calculate? Let me get rid of this. Oh, no, that's not what I wanted to do. I need the eraser. There we go. Let me get a bigger eraser. What we want to try and do here is calculate. How do we calculate the centripetal force? Well, to do that, what we have to do is we have to take into account something that you guys have learned before, which is Newton's second law. Now, Newton's second law says that the net force on an object is equal to the object's mass times the acceleration. So the net force that an object feels, if it's accelerating, right? If it's accelerating, the net force that it feels is equal to the mass times the acceleration. Well, in this case, let's jump back to this. The net force for any object that is centripetally accelerating, for any object that's moving in a circle like this, the net force is always going to be the centripetal force, essentially, because these two things, if it's not, accelerating up or down, which in this case it's not, we're going to assume that it's staying on that horizontal plane as it's moving. It's accelerating inwards, and the acceleration is always in the direction of the net force. According to Newton's second law, the acceleration is always in the direction the acceleration is always in the direction of the net force. And so the net force in this case is the centripetal force. So what we can do is we're going to kind of rename this to work for our circular problems here. So we can say the net force in all of these cases, these circular moving cases, we can say the centripetal force is equal to mass times the centripetal acceleration. And so this is kind of going to be our equation, our base for solving problems like this to figure out what is the centripetal force. I can use Newton's second law for that. So actually, let's use this for example. Let's something from last week that we used. Let's say that I knew for this right here, this yo-yo, let's say or whatever this object is, let's say I knew the mass of it was 0.013 kilograms, okay? And let's say I knew the length of this string, which we're just going to call the radius, right? It's the radius of this circle. The radius is 0.93 meters. And let's say I know the time that it takes. I time this, and I know that the time that it takes for this yo-yo to move one time around that circle is 1.18 seconds. So let's say that's the information that I know from this. And I want to figure out what's the centripetal force. So last week we learned how to solve for the acceleration of this. Let's figure out, can we solve for the centripetal force that the yo-yo feels? Well, looking at our equation, the centripetal force is equal to the mass of the yo-yo times its acceleration. Well, I know the mass, but I don't know the acceleration. So we're going to have to think back to last week. What is the centripetal acceleration equal to? Well, we learned last week that centripetal acceleration is equal to v squared over the radius. Velocity squared over the radius. Well, I know the radius, but I don't know velocity. So we have to take into another thing into account here, which is how do we know the velocity of this, which is another thing we learned last week. How do I figure out the velocity of this? And I'm just going to insert what we learned last week right in for this. We know that the velocity of this circular moving object is equal to 2 pi r over the time. So this is velocity. So I'm going to take that, substitute that in for v over r. This has to be squared because it's v squared. So 2 pi r over t squared. So this is the velocity of that circular moving object, which is just 2 times pi times the radius divided by time. So now if I simplify this, so if I square this over r, what I'm going to get, so if I square this and cancel out one of those r's, I'm going to get centripetal acceleration is equal to 4 pi squared times the radius over t squared. So there's my just rearranging some stuff basically. Since I don't know the velocity right off the bat, I'm just going to substitute this in for v, basically. So I've rearranged that equation to look like this. Centripetal acceleration is equal to 4 pi. 4 times pi squared times r divided by t squared. So now what I can do, I know the mass of this, and I've got this for the acceleration, so I'm just going to take this right here. I'm going to put that in for acceleration. So actually I'm going to give myself a little more room because I'm probably going to run out of room here. I'm going to erase this. Okay. So let's see. We've got centripetal force is equal to, it's going to be mass times, so this right here, our acceleration, which is 4 pi squared r over t squared. And there's my equation, especially if I don't know the velocity right off the bat. If I don't know the velocity, I can just substitute this in for velocity, basically, to get my acceleration. And so here's another equation you may want to put in your toolbox there. Mass times our acceleration to give us the centripetal force. So let's plug in the numbers and see what we get for this. So mass is 0.013 times 4 times 3.14 squared times the radius, which is 0.93, all over t squared, which is 1.18 squared. There's my big ugly equation there. Go through, crunch the numbers on this, and we should get, for centripetal force, 0.34 newtons. And it would be inward, we could say, the direction. This centripetal force is inwards towards the center of the circle, and that would be the final answer for that one. Hey, let's do, I know we've already gone on pretty long here, but let me do one more example with this, a slightly more difficult example here. And let's say we've got a car. We've got a race car racing on a flat track, and they tell us that the car is going 32 meters per second around a curve, and the curve is 56 meters in radius. What would be the minimum coefficient of static friction between the tires and the road that would be needed for the car to round the curve without skidding? So this is maybe slightly more, a little more difficult than the previous problem, but we have the tools to get it done. So if we look at this, we've got, let me draw it like this. So looking at it from the side, so let's say this is the back of the car. Okay, here's the top of it. This is like if I'm like standing directly behind the car, this is the back of the car. Here's the wheels. All right, and it's on this curve here. Should have drawn that more flat because they say it's a flat track. It's going around this curve, okay? And as it's going around the curve, right, we know that the forces that it feels are the normal force from the road, force of gravity, and it's going to be feeling, well, the centripetal force towards the center, but in this case, the centripetal force would be from the road, the force of friction from the road, right? Because the car, as it turns, it's going to want to continue off in a straight line, but because of the force of friction between the tires and the road, the force of friction is pushing it back in. So the force of friction is our centripetal force in this case. All right, so we've got that. Let's just write down the equations that we know we're gonna have to use in this case. So we know that we're going to need this right here, the centripetal force. So centripetal force, in this case, we're just going to replace it right away with the force of friction because that is our centripetal force. So the centripetal force is the force of friction, which is equal to mass times centripetal acceleration. So there's one thing that I'm going to need. Now, the problem is actually, it's not asking us to calculate the friction or the centripetal force. It's actually trying to figure out what's the coefficient of friction, that I need between the wheels and the road. So we're going to have to kind of think back to when you guys learned about friction and how do we figure out the coefficient of friction. And that equation is force of friction is equal to mu times the normal force. So I'm probably going to need this at some point as well, since this is really what the problem is asking for. It's asking for the coefficient of static friction. So I'm going to need this probably at some point. So let's actually try and figure this out. So I want to solve for the coefficient of static friction. So if let's say I rearrange this equation around to solve for this. So coefficient of friction is equal to, it's going to be the force of friction divided by the normal force. So these are the two things that all I really need. I just need the force of friction and I need the normal force. Well, let's see here. The force of friction, which is our centripetal force in this case, is equal to mass times acceleration. So let me replace this with what I know I can solve it with, mass times the centripetal acceleration. So force of friction is mass times centripetal acceleration. Normal force. How do I figure out the normal force? Well, in this case, it's just a car on the road, and so we know that the normal force is going to be equal to whatever the force of gravity is. So force of gravity is going to be the same as the normal force. So normal force is going to be equal to mass times g times negative 10 or negative 9.8 meters per second. So I can take this mg here, the weight basically of the car, and I can put it in for Fn here, so mg. And now if we look at this, the masses are actually, I don't need to know the mass in this case, because when I've got these plugged in, the masses are just going to cancel out. The only thing I need to know is the centripetal acceleration and g, and that's it. So let me plug this in now. Now here's the thing. Now we got another equation we got to bring into play here. We've already brought in 3 different equations here, but I need to know the centripetal acceleration. Centripetal acceleration is equal to v squared over the radius. So I can put this in for centripetal acceleration, v squared over the radius, all over g. And I actually am good to go with that because I know the velocity, 32 meters per second. I know the radius of the track, and g is just a constant, so I'm good to go. This is my equation. So I can plug in some numbers here. Is equal to, let's see, 32 meters per second squared over, the radius is 56 meters. So that over we'll just put negative 10 meters per second squared. Do the math on this, crunch the numbers, and we should get 1.8 for our coefficient of friction. So there's my final answer for that one.